Welcome to Modular March. I'm Andy, this is Robbie, and we are the Rollup.
Modular March is an educational experience about all things modular. Enjoy.
Welcome to Modular March. We have another episode today with Nick Dodson, the CEO of Fuel. Of course, joined with Rob, GM Rob, and welcome, Nick.
Hey, how's it going? Should I do a quick intro on myself?
Sure. Yeah, sure.
All right. Yep. So I'm Nick, the CEO of Fuel, and very, very happy to be here.
Awesome. Yes, stoked to get into this presentation. Let's do it.
Awesome. All right. Well, so for today, I thought we'd go deep into some of the problem space, and then kind of how Fuel is approaching solving some of the current problems in the landscape right now, and how we're thinking about building things. I'm sure, given the amount of presentations you guys have been doing, for Modular March, I'm sure there's like a ton of content already on like numerous topics. So I'll try to be brief with the problem section, and then just try to go heavy into some of our solutioning. But yeah, so let's dive into it. So first of all, the problem. So right now in the rollup space, just to dive right into it, it's 2024. We're doing a lot of rollups now. There's a lot of new different chains coming out. There's a lot of new architectures in the space. Basically, you can kind of briefly categorize the architectures that are in the space into two sort of broad categories. One of them is, architectures that were really designed for monolithic layer one blockchains. So, if you're familiar with monolithic and modular architecture, you know that that's sort of like layer ones that really are trying to design for everything. And effectively, the EVM fits into this category. So does Move, and so does the Solana VM. In a sense, these are architectures and virtual machines that were really designed for monolithic chains. And on the other side of the spectrum, you have arbitrary computing environments. And so in that sense, you have things like WASM and MIPS and RISC-V being used. So a lot of the architecture right now for rollups in 2024 is really divided along these two lines, right? And, when we get into just thinking about this problem some more, you can kind of see in the current rollup landscape, most chains right now are using either monolithic layer one or some kind of mixture of an arbitrary computing environment and monolithic layer one. Maybe there's one or two that were really designed for the tasks that we're really doing with rollups like Starknet, but the rest of them are really using architectures that we've seen in the space. And that makes sense. You see the EVM out there, it's everywhere. So there's a big business model around it. Same with Solana, same with the MoveVM. So it sort of makes sense from a business perspective to do this. But of course, a lot of these architectures were never intended to be used in what we now define as rollups. So maybe a helpful analogy for at least how I see some of the problem transpiring in the space. So like a simple analogy would be like you wouldn't put Windows like desktop on a phone. It just wouldn't make any sense. Windows desktop not configured for your hands, not configured for mobile networking, not configured for a ton of stuff that you typically experience with a phone. And when you look at the way something like an iPhone's built or an iPhone's constructed, they constructed everything around exactly how it's used. They constructed everything around, networking, around the fact that your hand is touching things, the fact that, there's certain battery constraints, right? And so it brings up this bigger problem, which is we're using all these monolithic layer one architectures, or we're using these arbitrary computing architectures, but we're using them for something that they weren't really intended for, which is rollups. And so the analogy sort of holds here like that. And to bring up some useful tweeting, basically when we look at the constraints, we look at the current space for rollups, we're starting to see that people are figuring out that, you can't just get everything you want out of the existing architectures. So nothing is magic and nothing is for free. And basically, we probably talked a lot about, parallel execution. You probably talked about a lot of things like state bloat and other things with previous podcasts. Well, they're all interlinked and they're all a really complex set of problems. And when you're reusing these previous monolithic designs, you're going to inherit all of the same problems that they have. Nothing's for free. Nothing's really changing. And you can't just magically, turn up the dials and say, well, it's a roll up, so everything's fixed now. And so
Nick,
a way to, yeah.
If you don't mind, would you mind breaking this tweet down for like a 5-year-old?
Sure. Yeah. So with rollups and particularly blockchains, we want to do a lot of transactions. But unfortunately, when you start doing a lot of transactions, there's problems with that. So for example, if your system's designed where a lot of transactions basically depend on each other, we call this like state or state contention. Basically, you have problems with just managing what we call like the statefulness of a blockchain, but you also have problems with incurring state. So if you're making tons of transactions, that's great. Well, now you have tons more data to store. You have tons more things to keep track of. You've so much more stuff that could depend on each other that could basically bottleneck a system, right? And so effectively, when you have a very high throughput blockchain, well, there's side effects to that, and there's problems with that. And really, if you don't have a good strategy for how you're going to manage the state of things, right, which is just, you have this, I have this, and as well, if you make a transaction, I make a transaction, and they touch the same piece of state, how are you going to deal with all of that, right? So both state contention and this sort of like big bloat of state that we're having with blockchains is causing a lot of issues. And so really, it's not so much that you can just do a lot of transactions. That's fine. You can design a system. You could write a Python script tomorrow that does a lot of things that look like a transaction and process that just fine. The big question is like, what are really all the side effects of this? What do you really need to run this system? What do you need to keep track of? What are all the interdependencies? And unfortunately, for a lot of blockchains and a lot of designs, they don't really have a good solution for this. They don't really have ways that developers can fix some of this stuff. So, it's one thing to be like, well, I can do a lot of TPS. Well, sure, you can write a server tomorrow that does hundreds of thousands of TPS, right? But the design of the system, the way that it works, is actually the most important thing if you want to build a blockchain, if you want to build real decentralized networks. And that's no different for layer ones. It's no different for rollups. So, maybe that's
Nick,
an explanation.
Quick clarification on the state bloat. It does historical state contribute to the bloat, or is it? Yeah.
So I would say that there's a few different ways to think about state. So really, when you're thinking about the problem, you're thinking about a few different things. One is, what does the node need to keep track of right now in order to progress things, right? So what does it need to have sort of on hand in its database to make sure that if someone makes a transaction, they can process it and know that it's valid? And then another side of it is, keeping all this historical information over time, which is more like what you would do with things like archive nodes and stuff like that. So archive nodes are, they're part of a lot of normal blockchain architecture, but they're sort of separate. Whereas state is sort of like, what does the node need to keep on hand in order to progress things into the future, right? And that's like, what does it need to keep in a database effectively? So for typical blockchains that aren't ZK, this is what you'd have to deal with continually. And even for ZK, you would still want the state information because you would need to know how to build new state in the first place. So both systems actually have to keep track of state in this way. If that makes sense.
Got it. Thanks.
Cool. So, so one way to think about this problem, this is like a helpful way that we've described it, is trying to solve for PSI. So performance, sustainability, and interoperability, right? You want your blockchains to be super performant, super fast. you also want them to be sustainable. Like, you don't want to run a supercomputer, right? And I think a lot of the negativity around certain chains is that effectively their node requirements are too high, and they're running what is effectively like a supercomputer. And there's no plan for exactly how they're going to manage the database of those systems, how they're going to manage the state access of those systems. So they're very contentious, and they're very large. And then as well, you have to manage for interoperability, which is really a new thing. You want blockchains, particularly rollups, to be able to talk with each other, and you want them to be able to introspect each other, and you want to be able to go over on one rollup, make a swap, go over to another, do some lending, come back and do another swap. Probably have that happen in a very short period of time, or in the same block, for example. So you want to be able to do these things. So we want to solve for these particular problems, right? And unlike sort of traditional problem solving that you've seen in the space, you actually want to solve for all three. So this is what I sort of describe for as like the Rollup Trilemma, which in the blockchain trilemma, where it was like decentralization, security, and performance, which is like a little different, where they were like pick two, in this case, I'm going to say you actually want all three, and you just want them. So there's no pick two here. It's just pick all three, or nothing, basically. So you want rollups to be super fast, you want them to be sustainable, and you want them to be interoperable. And in the state of the architecture nowadays, like, everyone wants all these things. So for this, I call it the Rollup Trilemma. And to look at sort of the landscape of what's happening in the space, and I'm sure you guys have covered this with a lot of the modular stuff you've done. The landscape is like rapidly evolving right now. So there's tons of different execution environments. There's tons of different sequencing options, tons of different proving options, lots of different data availability layers, and lots of different settlement layers. So there's a crazy phenomenon happening where if you are building a blockchain as a rollup, you've got crazy amounts of options happening, right? And all of these will touch or interplay with effectively these things, right? Like, depending on what you pick, depending on how you go about it, it's going to affect any one of these things, right? So we've got this wide landscape of things happening, and obviously for a developer, this is going to be pretty daunting, right? And like, there's a lot of issues here in just what do I pick and how do I navigate this space, right? So there is sort of a need to bring some clarity and some harmony around how this is all going to work and what people can actually do with all of this stuff. So a helpful analogy here is we actually saw similar things happen with computing and also like the early internet. So you can think about different pieces of the stack as sort of different things that you would do with the system. So, some tasks are more like CPU, some tasks are more like networking, some tasks are more like GPU, some tasks are more like storage, and some tasks more like IO. And we've got users and we've got applications. And typically, how we've dealt with this in the past is we've built operating systems. So operating systems are this sort of low-level code that helps us just deal with all of these different things, right? They help us manage all this stuff so that when users are using applications, they're not thinking about like, oh, my CPU is too slow, or, I don't have enough storage. The users are just using applications in the space, right? And so similarly, we think of the rollup problem as a very similar issue, right? Where effectively you have users, you have applications, and you need some kind of operating system to really bring everything into order and design for all the problems that we currently see in the space, right? And do, the right thing. And so this is where we kind of get into a little bit more about Fuel and what it is. So Fuel is really an operating system for the rollup landscape and for the rollup space itself. So Fuel brings a lot of things to the table in terms of our virtual machine, our networking, our proving, or as well, the way that we do DA adaptation. And the idea is just that similar to how computers and hardware have an OS, right, that deals with, all the different tasks that your computer has to deal with, our Rollup OS does something very similar, which is basically just trying to say, hey, like, you're going to need proving, you're going to need really, a certain kind of state transition that works really well for blockchain. You're going to need bridging, you're going to need sequencing, you're going to need all these things. We will come in and we will harmonize all these things for you, right? And so in this sense, what Fuel's always trying to do is give you the right tool for the job. So something that's really going to come in and solve a lot of these issues that we experience in the space, and also just design things that are more harmonious with the current landscape and the current space. So we say the solution is really the Rollup OS itself. And so, to cover some of the things that we kind of bring to the table here in terms of the modular landscape itself. So Fuel has the Fuel virtual machine. We have a unique proving model, this is hybrid proving. As well, we have DA adapters that you'll be able to use to select whatever DA layer you want. As well, we have a very unique set of tools that allow you to build applications in a way that the space doesn't really offer. And then as well, we have a network. So a network of different rollups that can interoperate with each other and basically address a lot of the current problems that we see in the space in relation to interoperation. So to talk about some of the virtual machine and sort of how this works. So the FuelVM really, it packs a big punch, and it's really as well influenced and informed by all the previous virtual machines that we've seen in the space. So whether it's the Solana VM, the Move VM, the EVM, WASM, all these different VMs that we see in the space, we basically educated a design of all of those things into a single virtual machine. So we have a very highly performant sort of 64-bit virtual machine. It's capable of doing a lot of transactions. So, something like right now, at least, and it's unoptimized currently, so around 12,000 TPS per core. On Ethereum, if we're fully optimized with DA compression, something like 5,000 TPS for transfers. So it can do a lot of TPS, quite frankly. As far as the way that it works, Fuel and the FuelVM uses a UTXO model. So, if you've ever looked at or have seen Bitcoin before, it's something similar to that, but ours is much more advanced. So really we have, a UTXO model, but it works over not just coins like in Bitcoin, but it also works over contracts. So you get all the same things that you can do with the EVM, but you get this really unique sort of state access system that allows you to use both coins and contracts together in a single transaction. And you can do many different types with many different people owning many different things. So it's a really sophisticated transaction model in and of itself. And on top of that, you can do things like scripts, which we don't really have with Ethereum right now. And as well, you have things like accounts, which are predicated accounts. So these we call like spending conditions. And this enables you to do a whole crazy host of things. But before we get into that, I'm happy to pause here in terms of Fuel virtual machine stuff, and we could talk over that if we need to.
Before we get into the VM, I've got a question about the UTXO model versus the account model.
Sure.
My understanding was that Bitcoin wasn't able to have smart contracts because they have the UTXO model. So how are you able to get smart contracts using this UTXO model? What is your general thesis on why you chose this model?
Yeah, so I think that the UTXO model got a very bad rap, both from Bitcoin and from Cardano. So basically, a lot of the things that were said about it are not related to the UTXO model, but just the way the system's constructed. And thus, this huge problem happened where effectively the community blamed UTXOs for something that they didn't do. And then, we kind of had this divergence. But all UTXOs really mean is that you're just defining what areas of state you're going to touch, right? However you want to define that. And then you're going to produce something and you're just going to say, hey, I've changed all of these different things, right? So when you look at the inputs here, you're just saying, hey, I'm touching these coins and I'm touching these contracts. There's nothing crazy about that, but that's actually the UTXO model. And then when you have outputs, you're just saying, hey, I'm going to, send these coins here. I'm going to change these contract state here. There's nothing crazy about that. And there's no divergence from the Ethereum experience of smart contracts or anything like that. So you really get to have everything you ever wanted with the UTXO model with no downsides. Quite frankly, the only downside is that maybe it can use a little more data sometimes. But quite frankly, that's worth it because you want to define when you're processing transactions like, hey, this group of transactions touches this over here. This group of transactions touches this over here, right? And then you can say, send this to thread 1, send this to thread 2, right? And so when you have that, it makes processing super simple. And so, the UTXO model got a very bad rap. But quite frankly, it does nothing in the way of a transaction other than just trying to say, hey, I'm touching these things. Now, there's some subtleties, right? Cardano implemented too much determinism. So they basically couldn't build Uniswap because Uniswap has this contentious state that's like, the amounts in the pool. And you don't know what the final amounts are going to be when you're making a transaction. It's settled later by the block builders, right? So effectively, it creates this huge contention, and you can only make like one transaction per block per app or some crazy dumb thing like that. Now, we just didn't design it that way. So we just designed it with the similar way Ethereum does, which is basically just to say, hey, like, if you're touching this contract, then basically you can have 5-6 different people touch the same contract. We just order it and line it up in such a way that you don't need to know the final state of things until later on anyway. So there's no contention there, basically, even if you touch the same contract. So effectively, the UTXO model gives you what you really want, which is a state access list of what you're touching in state. And so similarly with predicates, predicates allow you to then take these things like coins here and then basically do like what would be considered maybe account abstraction over those coins. And you can just define like, what are my spending conditions? And a lot of the time, you don't even need to use smart contracts at all. You can just use predicates and use these stateless scripts. And you can imagine that like right now, we're processing maybe 50 to 500,000 people's transactions daily with blockchain, right? But imagine if you had the whole world running through these chains, like the entire world, right? Billions of people. You can't have contentious state. Like you basically, you would cause, it would be way too difficult for the system to have to comprehend all these things. You wouldn't want someone in India holding you up when you're making a transaction in, like Germany, right? Like it just would be awful. So you want to try to break away from using stateful smart contracts, and you want to go to things that are more lighter. They're easier to process. They're easier to handle. And so predicates give us that ability to kind of do this. And basically in the next slide, just covering some of the crazy things we can do with predicates. And again, this is without smart contracts. We can do things like multi-sigs, BLS aggregations, social recovery. We can support any wallet. So MetaMask, Phantom, Secure Enclave. We can do things like fee payers. So basically, pay gas in any coin. You can settle really complex trades, right? Really complex trading conditions as well. You can settle really complex intents, right? And the idea is that because we're designing for things like sustainability, we wanted to opt into these kinds of designs to say, developers really want these things. They actually want to build better systems that are more sustainable. They're lighter, they're easier to manage, they're easier to maintain. So predicates are really a part of that for us in our virtual machine design. So I can pause there, but yeah, hopefully that answers your question too.
Yeah, it does. And this is a special result of the FuelVM that you get both the UTXO model and the predicates.
Yeah, it's basically everything coming together into one really nice package. So we're taking the best of Bitcoin, we're taking the best of basically Move, you could say, the best of a lot of these different blockchains and putting them into one architecture and making that into something that is actually pretty special. So this is on the virtual machine side. So just touching on some of the things, there is way more stuff in the FuelVM, but just wanted to touch on a few things. To go into more of the proving side. So basically Fuel uses what we call it's like an optimistic and ZK hybrid. So essentially we combine both techniques together, where if you have an invalid block, you just submit it to a ZK proof. If it proves that the fraud is, is there, then you just remove that block. But you just keep producing new blocks from the most recent valid block. And so the system really never stops, but effectively you have this much easier way to prove that a block is invalid. This also gets the Fuel architecture ready for ZK, which we do really like, but we're just using a little more pragmatically, especially if our system's going to be doing, 12,000 TPS per core, for example. That's one core. So one core in your M1 can do 12,000 TPS. Now, if you do 8, you multiply that by 8, right? Now, to do that same work over a ZK requires lots of things, like a crazy amount of stuff. And
a whole warehouse.
Yeah, a warehouse. Now, mind you, that might work for certain things, and that might be totally fine for certain things. And ASICs and other things are going to come, all kinds of crazy stuff. But for now, Fuel is more pragmatic about how we want to use proving in ZK. So for us, like, we'll use it right now when things are invalid. Eventually, maybe as they get more efficient, we'll use it for when everything is valid. So basically, just using the technique in different ways. But yeah, the idea is we have a much more simplified game. It's a single round game. And when there's an invalid block, just prove that, slash the block, keep going. So this allows us to do a few things, like we can reduce eventually bridging time down. And as well, I also released a paper on research on what we call fast finality optimistic rollups, which effectively can get the finality of an optimistic rollup down to potentially even one Ethereum block if you have the right kind of design in there. So essentially, we have lots of different ways to make optimistic rollups into the system that we really want to see. But ZK is playing a role for us in multiple different ways. So yeah, that's just like a, I can pause here as well, but yeah, happy to go into this.
I got a question here too, and your answer might just be go read the paper, but like, it is one way to think about this essentially that it's an optimistic rollup, and then there's a fallback to ZK in the case of essentially that 7-day dispute window that no one really likes and no one really takes the canonical bridge because of that 7-day dispute period. You basically have the optimistic settlement on the L2, and then in that case where you're either going back to the L1 or in the case where someone calls dispute, that's when you fall back to this ZK proof to prove that the fraud is there and invalidate that or reorder.
Yeah, so let me describe a few different things. So with this, there's a lot of nuance. So basically, the way to think about the 7-day window is sort of, it actually doesn't have a lot to do with the mechanism itself. So whether you're using the CK dispute prover or you're using just a pure IVG model like what Optimism is implementing or Arbitrum, the 7-day window is really just, you're trying to give enough time to submit a transaction to say, hey, there's something wrong. And then you go through the whole process of the game, right? But unfortunately, the way that Ethereum's designed, if someone just fills up Ethereum blocks for a long time and you make that window too short, then basically you have this big issue where like you can't get in the flag transaction to say like, hey, there's something wrong. You can't get it in. So an attacker, a smart one, could basically attack all these systems, right? So this mechanism is just trying to simplify the 7-day window down, sort of in a sense of we know we can probably safely get the window down to 24 hours, regardless of the mechanism, just to try to do that. But the finality post that I made is actually a little different. The finality post takes the optimistic rollup on its head, and it sort of says, well, instead of trying to submit a transaction only when there's fraud, what you do is you have everyone submit constantly that their things are okay. And if one of those transactions is missing, then you know that there's actual fraud and you start expanding the window passively. So you flip it on its head, and then that way a censor can't censor you. So it's an interesting post. It's definitely going to be part of our sort of finality model for offering Fuel rollups. But the idea is just that when you flip it on its head, you no longer have this censorship issue, because you're basically saying if there's a missing transaction, then we assume censorship and the window just passively expands up to something like 7 days. So basically, this allows us to do some pretty wild stuff. Like you can have many different optimistic rollups that are coming to finality, effectively like a soft finality, just so long as everyone checks in. All the different validators in the pool check in. So it's a slightly different model to what's described here, in the sense of this is just for voting and progressing state. But the whole idea is just that the combination of these techniques can allow us to really significantly reduce the finality time of optimistic rollups, which was a huge burden before, because it was like, you want to deploy an Arbitrum layer 3, well, you got to wait 7 days to withdraw out of that, right? It's like, that sucks, But now actually with fast finality optimistic rollups, and as well using things like these ZK techniques, you can simplify the actual game, and you can lower the finality window. So I didn't really cover that too much in this because it's still sort of like active research, but the idea is just to say that we have the ways now to do a lot of different really cool things. And as well, even that other technique does use ZK. So it's not to say like gets rid of ZK. It's just to say we use it slightly differently than ZK rollups right now. Yeah. So that's on that point. But there's sort of a difference between the proving mechanism versus like the finality window and the challenge window and that sort of stuff. Like they're kind of separate. Yeah. Cool. So in terms of DA, as well, like Fuel will aim to support all of the common DA layers that you see. So our first one's going to be 4844 DA, but of course we'll allow for options for Celestia and Avail, Eigen DA, Near DA, all the other kind of DA layers that are out there. So we'll have full DA sort of adapters for all these things. Right now, we just got to focus on Ethereum as we get our first layer 2 out. But we'll allow for these other DA options after. On the tooling side, we also have our own language. We have our own tool chain called Fork, and we have our own infrastructure. So essentially, this problem of like having to go between 5 different tools or all these different, pieces of infrastructure, etc., is now completely simplified. So when you have your own language, it also means you can do everything. You can do testing, do deployment, you can do indexing, you can do everything with the one language. So Sway will really be sort of the ultimate blockchain language that people can use. And Fork will allow you to do it all in one tool chain. So you don't need to have 5, 6 different tool chains. You can deploy an app with that. You can deploy a rollup with that. You don't need to go anywhere else as a developer. It sort of answers all your questions. And then as well for Fuel Infra, all these other things like providing really rapid soft confirmations, providing all kinds of different data and streaming infrastructure, all the things that you typically see with blockchains, but providing that for a very high throughput chain. So doing it for the EVM is one thing. It's like 15 TPS. Doing it for something that could do, thousands of TPS, it has to be designed a certain way. So we try to provide all the necessary tooling. And especially with our language and, all the different attacks you typically see with Solidity and everything else, it's nice that you have a different blockchain language that tries to address some of these problems. So on the right is all of the reentrancy attacks that have happened on Ethereum. It's not all of them too. It's just a section of them. And then on the left is a smart contract with reentrancy inside of it. So naturally, when you're designing a language for a blockchain, you want to address some of these things, and Sway does. And Sway brings a much simpler kind of system or interface to the table. So full standards being available for everything, as well like reentrancy preventions is provided in the standard library itself, and just bringing in all the new things that we know about language design into the table, like traits and all this other stuff. So it should be a very fulfilling language for developers to use, and something that they can be really productive in really, really quickly.
Nick, real quick on the Sway part, forgive me for my lack of programming knowledge, but isn't creating your own language risky? And also, isn't it just recreating the same problem of Solidity, where it's like users devs have to go and learn this entire new language and kind of start from scratch versus something that they may already know?
Yeah, so I think there's a few points to that. So one is that it's not inherently that Solidity is bad because it's a blockchain language. In fact, I think that's one of the best things about Solidity is that it is designed for what it's for. Now, mind you, because of the way the EVM is constructed, because of the way Solidity works, sometimes it's really hard to pick up things like reentrancy with it. And as well, the language was designed iteratively over time with many different code maintainers. So it kind of succumbed to a lot of like grammatical complexity that it might not have needed to. But Solidity actually, its problems are basically that it didn't have other great languages to look at. And I think Rust was still a developing language at the time. So it couldn't really model itself after something really strong. Now, on the flip side, if you do use Rust to make smart contracts, it's also horrible in a different way. So when you use Rust or C to write a smart contract, those languages were really designed for systems, like they were designed for systems programming, right? And when you use something, again, that's not designed for what it is, you end up with this like super band-aided mess where like Sway right now looks like you're only writing what you really need for your smart contracts. You're only defining and setting things up for exactly how the thing works. With Rust, it's like you have 5 million different annotations. You have like 10 different ways that you need to constrain the system just to make it work properly. And that's because it's not really designed to build smart contracts. It can, but it probably isn't the best tool. So Sway tries to mediate between all the things we learn from Solidity, all the nice things we learned from modern programming in Rust, and it tries to give that to a developer. And quite frankly, learning Sway is going to be really easy for someone with Solidity because you have things like a blockchain language that's designed for things like storage and ABIs and everything else. So that'll be very familiar to a Solidity dev. Like they'll look at this and be like, takes 2 seconds. And as well, similarly with Rust, like they'll be very familiar with the syntax and the intention of the language. So effectively, you might think, yes, it is more risky, but actually all we're doing is bringing the best stuff from what we saw with previous blockchain languages, the best stuff from Rust, and trying to bring that to a dev in a way that makes a lot of sense and is actually designed for the job of building these smart contracts. So yeah.
Are there trans compilers that, like, if I want to write it in Solidity or Rust, or hypothetically, even if I wanted to write something in like natural English language, like it'll just kind of translate over?
So I really shouldn't do this, but I could share something if you want to see something.
Yeah.
Okay, let me see if I can share my screen real quick. Okay. So this we haven't released yet, but you can use it right now. Let me just present my screen for a second. Okay, so here's Sway Playground. So this is actually public. You see my screen?
Yeah.
Yeah.
Okay, so you can actually just hit this Solidity tab, and we actually have these full transpilation demos now. So you can fully transpilate. Here's Solidity on the left. Here's the Sway on the right. And again, this is more educational. So here, I'll pick an ERC20 token. So you can see like Sway is actually pretty nice language in the sense that because we took these nice things from Solidity, we actually have a much easier time transpilating the logic over. So this we haven't launched yet. So I guess just don't bring it up too much in the tweets. But yeah, this is really meant to try to train Solidity devs into Sway really quick, right? And make that process super simple. Awesome. So anyway, and we'll have a lot more really dynamic translation later as well. So it'll only get better from here. And as well, we also want to have Sway target other backends. So there's all kinds of blockchains that could really benefit from a front end like Sway, basically. So like Aztec or Maiden. It's really hard to build a language. So we spent a lot of time on this. So basically, I think they could benefit from it if we could get it to work. So anyway, that's maybe a sneak peek. Very cool. But yeah. So you can take a look at that. That's like sway-playground.org. Cool. Okay. Oh, any other stuff on Sway or next slide?
All good.
So so the last thing, which is also a little bit of alpha, is we actually are putting together a sequencer for Fuel 2. And the sequencer allows for the sequencing of both block production and transactions over many different rollups. So the idea is that Fuel has a very special virtual machine and has a very special kind of transaction system. And we can really create a lot of interesting advantages with this at the sequencing level, where blockchains can really actually look at each other and talk to each other if you're putting the transactions in the same funnel. And so, so Fuel will have its own sequencer, but we'll always allow people to pick the sequencer they want. So if they want to use Espresso, they want to use a combination of like Espresso and Fuel sequencer, they'll be able to do things like that. And so effectively, we want to give people as many options as possible, but we also want to offer our own selfishly, because we think we can offer a lot of really interesting design patterns and value. So basically, when it comes to producing blocks for different rollups, you would have the transaction go to the builders. The builders are then going to either via an auction or depending on how the rollup's set up, many different models are then going to decide the sequence. And then that basically goes into execution and gets passed off, or it gets passed off into just going down the bridge back to Ethereum. So this diagram is not the best diagram because it goes from sequencer to rollup, but the point is just that contextually speaking, you can have these fuel builders. They could build for potentially different rollups, and you'll have sort of a system in which rollups can not only have blocks being built for them, but also they can interoperate. So the rollups can see each other and they can introspect each other, which is something that you want to do as fast as possible, and you want to do basically at the earliest possible stage. And so with Fuel, you can have two different rollups that are basically looking at each other's block construction. They're looking at each other's block design. And then they're basically like filling in different information from different chains. And given the way that predicates work and other things in our virtual machine design, you can basically have things like trades that settle when certain trades happen in different chains. You can have all kinds of sort of instantaneous interoperation going on. And when you mix these models with things like our fast finality gadget, you get this really crazy sort of system of rollups that we just haven't really seen yet, because we've been working with the EVM, we've been working with Move, and these VMs are not really designed in this way. So for Fuel, because we design it from the beginning this way, interoperation is going to be really smooth, and the sequencer is going to help with that process.
Gotcha. Nick, real quick there, if you don't mind.
Yeah.
The big sequencer situation is, why use decentralized shared sequencers if you're a rollup operator? Why give away all your revenue? Espresso's like, no, you don't have to. Astria's like, no, you don't have to. NodeKit, etc. So that problem is kind of being solved by the shared sequencer level, in essentially it's being thought of and iterated on. When it comes to Fuel sequencer, what is going to be the financial or economic situation between rollup operators and Fuel, kind of DAO, or however we want to overlay that?
Yeah. So I think with sequencing, there's a few different things. So most blockchains are not dealing with what Fuel's model is, right? And so they're not really set up for that. Now, they might say they are, but if you ask someone like Josh, they'll be pretty honest with you and be like, we're mainly doing the EVM right now, right? Which means that, for a new architecture like Fuel, it's pretty rough to actually get the kinds of things you want inside of a sequencing environment, right? And secondly, sequencing can happen in a more additive way. So when we decided to go down the route of doing a sequencer, we know that we probably could at different stages tap into other sequencers for different things. And so I actually think that sequencing can happen over a bunch of different layers and not just have to happen through one specifically. But moreover, there's a lot of different kinds of design that we wanted to do with UTXOs that are sort of settling in a stream format, you can say. So long before it ever gets to, Ethereum or like a final settlement layer, almost at the mempool level, there's kinds of trades and settlement happening via UTXOs and via predicates. And that's something we uniquely can advantage, right? So for Fuel, as we build out our architecture, we want to really be able to have apps and devs really advantage that, because it's really the fastest kind of trading, the fastest kind of transactional design you can possibly do, right? It's way before it's almost even in a blockchain. You're already settling things, you're already moving things around, right? Like as high frequency as you can get it. So the reason why we wanted to do our own sequencer is because we wanted to really, show off, you could say, all the different things that Fuel can do. But also because at a very basic level, we just want to decentralize our block production. And quite frankly, for the kinds of architecture that we make and we build, we'd prefer to be able to tweak that pipeline so that devs get the best experience, users get the best experience. And of course, we'll always offer other sequencers as you try to deploy rollups. So you don't like it, you want to use Espresso or Astria, go ahead. I think it's just, we want to really have the best showcase of our tech. So maybe that's the answer. Yeah.
Cool. Alrighty.
Awesome. So I only have a few more slides left, so it's closing out. But yeah, so to kind of sum it up, we have a whole suite of tools. We have a whole set of architecture for rollups themselves, all designed to really meet a lot of the problems that you see in the space. And basically, we try to address a lot of these problems with just good design, whether it's like performance, where we have the VM and the transaction model, or sustainability, which is more on the transaction model and the predicates, or interoperability, which is like the transaction model and the sequencing. We try to provide the developer a really comprehensive operating system to really build incredible rollups, and ones that can, scale, they can perform really well, and they can also be very, very sustainable. And you could just imagine systems both like Conduit and also something like Fuel as a Service, where you just select the sequencer, select your GA layer, select your proving model, deploy, it's done, and you have rollups that can do 12,000 TBS per core. So it'll be a pretty wild reality for that, and it's already starting to happen with other architectures. And really, between these different tools, these different ideas, we want to really comprehensively solve a lot of the problems that we see in the space with, again, good design, good architecture, and yeah, that's basically end of presentation. Yeah.
Well, you better watch out, because Josh is coming for all the RAS providers. So FAAS has got a hothead coming for him.
I believe it, but I know all of Josh's weaknesses, so it's okay. We every time we meet at a conference, we have a good conversation. So yeah.
Good, man. We really appreciate you coming on and giving us a live demo, a full conversation, and answering some of our questions for sure. And yeah, I guess the last question that we have, which everybody has for you and Fuel, is WEN, when?
Yeah, so soon TM, and like if you go back into like old Ethereum folklore, it's like two weeks TM is the statement. So yeah. They said good. 2 weeks TM, and it took them another 8 months. So something like that.
So somewhere between 2 weeks and 8 months sounds
right.
Sounds like a plan.
Yeah.
All righty,
yeah.
Nick. Thank you, man.
Awesome. All right. Thanks, guys.